So what inflation really predicts is this: anything can happen. So what about a theory that says anything can happen? Is that a problem? Yeah. I'd say it's an unmitigated disaster. That's a theory that is maximally unpredictive, maximally untestable. There is no test that you can possibly construct which could disprove this theory. Because anything that you would observe by a test is physically possible, and anything that's physically possible can occur and will occur in the multiverse an infinite number of times. So we've constructed a theory, not on purpose, but by accident. We've constructed a theory which has devolved to a point where it's completely untestable. Now, to consider such a theory is a really radical thing to do in science. Although some people are saying that thinking about inflation is conservative, I would argue it's extremely radical to consider the possibility. Because everything we've been doing in science, in fact, the whole view of science, since it was since humans first invented it, around the time of Galileo, everything has been aimed at the idea that observations and experiments are key to testing our ideas. Theories have to come up against tests over and over and over again. That's how we gain confidence in our ideas. This is a theory which is fundamentally untestable. So when people, Max or anyone else included, claims that there's data or support for inflation, the thing you should do is raise your hand and say, but doesn't inflation produce a multiverse in which anything could happen? So what does it mean to say that it supports it? Or if people say there are tests that you could do in the future that could disprove it, raise your hand next time and say, what about the multiverse? Isn't it true that there's no test that could possibly disprove it? Because if you observe it, it must be possible in the multiverse. It's a fundamental problem. It's a kind of breakdown in a theory that we're not accustomed to. Most of the time when we talk about theories breaking down or theories having a problem, it's because it actually makes a prediction. You go out and you test it, and the test is not consistent with the prediction. We're used to that kind of breakdown. This is a different kind of breakdown where you thought this theory was predictive when you started, but by the time you ended up understanding it properly, it turned out not to be. Now, this doesn't mean that theorists have settled for this. That's why the theory is still around today, because that myth, that idea, before we understood about eternal inflation, before we understood about the multiverse, that myth that expansion could help solve our problems is so compelling, so appealing somehow to our intuitive sense. You'll do anything you can to try to save this idea. So theorists have been working hard for 30 years. They haven't sat still on this. It's been a small group of theorists that have tried to think really hard how you might save this idea. And the one idea that they've come up with is the idea that's sometimes called the measures. Sometimes they call it the measure problem. It sounds like a rather abstract, kindly little problem, but actually introducing measures is actually a really big deal into this story. So the idea of the measures is this. Okay, we have this eternal inflation. It produces this multiverse in which anything can happen infinitely many times. I will now add a little rule, a small little rule that tells me how to weigh these bubbles, how to count these bubbles, hopefully with the idea that I will be able to argue after that bubbles that look like us are more probable than ones that don't look like us. That would restore the theory to predictive power. Okay? So that's the idea of what we call measures, whenever you hear that. Among these measures is what's sometimes called the anthropic principle. We include anthropic reasoning, or the fact that we exist becomes a selection principle in helping choose some bubbles over the other. I just think of that as another kind of measure. So what do we say about this? Well, the first thing I think to be said about this is before you even consider the idea, recognize what you're doing. What you're doing is taking a great leap backwards in the following sense. Why did we invent inflation in the first place? Well, because coming out of the Big Bang, coming out of a sudden bang, a sudden quantum origin, we couldn't understand how we'd ever get the simple, smooth, flat conditions we observe in the universe in the large. It seemed that it was unlikely. So we invented inflation so that inflation would give us those conditions. But in fact, what we found is it doesn't give us those conditions, or at least not only those conditions. It gives us those conditions and every other possible condition, including a universe that is not smooth and a universe that is not flat. So we're actually back to where we started before. When we started before, we said coming out of the Big Bang, anything could happen. And now we're saying in the multiverse, anything could happen. We're back to where we were before. We need some idea that selects from this what is more likely, or forces things to a condition that we observe. So we've made no progress at all. So by the great leap backwards, I mean you have to now admit, if you're going to start down this path, that inflation has done nothing at all to solve the conditions you were trying to solve. It just transformed the problem from thinking about a single bang to now thinking about a multiverse of bangs. Okay? No change at all. Anything that you now add to the theory is where all the power of your idea is going to come from. It's not coming from the inflation at all. Inflation just helps set the tables. Now, what about the second problem with this idea? The second problem with this idea is that the most natural measures, when you try to introduce a measure, fails miserably. So think about this picture of a multiverse containing an infinitude of bubbles. And suppose I were to ask you, what criterion might you introduce as a measure to decide which is more likely? Anyone have any suggestions? You're trying to decide which bubbles are more likely. There's an infinitude of each of them. We're going to make a rule. We're allowed to make a rule to decide which is more likely. Anyone want to?
The one that happened.
What?
The one that happened.
The one that happened. Okay. Okay. But that would be a rule that just says, okay, that would be a rule say you observe what you've got, and you say that occurs somewhere in the multiverse, but it doesn't tell you the probability of it happening. So it's not really a measure. Yeah. I want to measure. I want to measure that I want to then conclude that the one we observe is the most likely. So what would be a natural measure that you might choose? Common sense. Any ideas? Everyone's afraid to answer this question. This was not supposed to be a hard question. Well, I would say a natural measure is you might ask, where's most of the volume? What kind of bubbles occupy most of the volume? Or you might say, which kinds of bubbles occur most frequently? For example, the flat ones occur more frequently than the non-flat ones, or something like that. Or ones that are, like us, more frequently than others. Well, if you introduce that kind of measure, you can actually then calculate the likelihood of our existing in the universe, and the likelihood turns out to be something like, once again, 1 part in a Google Minix. Very unlikely to have something like us. Very unlikely to be in a patch of universe, for example, which is as old as us and has the billions of galaxies that we have and all the properties that we observe. One reason that contributes to this huge unlikeliness is the following fact. Let's think about these bubbles. These bubbles were being produced at different times in the history of this inflationary universe, and so that we can talk about bubbles having different ages. Our bubble would obviously be about 13.8 billion years old, because when we measure the age of our universe to be that age, what it means in the inflationary picture is that's when our bubble formed, that long ago. Then let's think about bubbles that are just 1 second younger than that, just 1 second younger than that, but have all the other properties that we have. Okay? So they have all the stars and galaxies and all the physical laws and all the other properties we have, but they're younger than us. Those bubbles are exponentially more likely than we are. Exponentially. Why? Because during that 1 second, the universe underwent during the second between when our bubble formed and those younger bubbles formed, the universe underwent a huge amount of inflation. There was a whole bunch more volume in which to make bubbles, and therefore more bubbles of that younger age were made. In fact, the factor is something like 10 to the 10 to the 35 bubbles of those bubbles were made more than bubbles like ours. And then, if you, of course, why does it have to be 1 second old? It can be 10 seconds old, or 100 seconds older than us, or 1 year younger than us. And those add up, and that's how you build up these incredibly small likelihood of us compared to, and I'm just talking about the subset of bubbles which are like us in every other respect except for age. So we are very unlikely in this picture. And you can't use anything like anthropic reasoning in this case, because there's no problem with having a universe which is like us, but 1 second younger. We would certainly exist. Yeah, we'd certainly exist 1 second younger than we do today. There's nothing anthropic. There's nothing about a universe that's 1 second younger that would prevent us from existing, since we were here 1 second ago. So this defeats all these kinds of measures. So what that's led to is theorists trying to invent other, more complicated measures that would favor us relative to the alternative. The natural measures don't give the right answer, so let's make a more complicated measure. And I'm not going to tell you about all the other measures that people come up with, but the point is that if you begin to consider other measures, what you find is, well, not surprisingly, any prediction or predictability of this model is going to depend entirely on your measure. If you choose some other way of measuring things, you'll get a different prediction of what's more likely than if someone else chooses a different way of measuring things. It has nothing to do with inflation. It has everything to do with your choice of measure. It's not a physical theory. It's just a choice of measure, owing to the fact that you had a theory which broke down in this form of multiverse and extended inflation.